Alright, let's take a look at another combined loads problem and finding stress for a case of combined loads. So here what we have drawn is sort of this elbow shape thing, and this has a circular cross section, and the radius of that cross section is r. And then I drew a coordinate system here on the right just to make it clear what direction this force is acting in. But this force is acting in the z direction, so coming out of the page. And we're interested in finding the stress at this point A, which is down here at where this elbow shape meets the wall, again with a fixed boundary condition. And we want to find what the stress is at point A. So from our point of view, this is at the top of that this tube. So the distance between the wall to where the force is acting is L, and then we actually need one more distance in here, which is this height h, which is the distance from this midline to where the force is acting. Okay, so once again, we'll need to draw a free body diagram. That's the first thing we want to do. So we're going to redraw this tube. So we're going to make a free body diagram. Let's show where we're cutting. So we're interested in stresses at A. So we're going to make a cut right there, right up against the wall again. And we'll redraw the loads that we have acting. Oops, lost the whole thing there. Okay. So what we have then, we know that we have this force Z, and again that's coming out of the page. So that means there must be an equal and opposite force going into the page, acting where we made our cut over here. So there has to be a force Z going into the page. Okay. Now this force Z is also causing a moment and a torque that's going to contribute to torsion, right? So there's going to be a moment about the y-axis because this force Z, if we're looking over at the left, this force Z would normally be causing a moment over here against the wall that's equal to that force multiplied by this distance L. Okay, so if we were to draw, this is our y direction, this force times L applies a moment that would be in the negative y direction. Here at our reaction, we're going to have a moment about that y direction, and it'll be in the opposite direction of our applied moment. Okay. Now there's also one other torsion that's going to be caused about the x-axis. So that force would be typically causing this pipe to rotate like this, looking at our left. So that means our reaction has to be in the opposite direction. And we will have a torque, we'll call that capital T, about the x direction, and it's rotating opposite to what the applied load would be. So if we were to, and recall that we're looking at this point A to calculate stresses. So if we were come down now, let's keep all of our reaction forces on one screen. We're going to use these reaction loads. So if we were to look into, if we were looking in this direction here, let's make that a different color just to indicate that it's not a force, we're just looking. But if we're looking this direction straight on to that circular cross section, then let's draw what we'd see. So we'd be seeing a circular cross section. That point A would be right here at the top, and it's right along the midline. So for bending, bending in the y direction, this would be along the neutral axis for bending about y. Okay, so now if we were to, and just to make sure we're all clear what direction we're looking, this would be our y direction up, z to the right. If we were now to take the stress element right there, and see what stresses we have. Okay, we know that the torsion, the way we drew that is acting like this. That would be the torsion. So that's what's twisting this tubular shape, this circular cross section. So you can see right away that there's going to be some shear from torsion, and it's acting right there on that top face in this direction. Okay, so from that torsion, you know that there will be shear to balance that torsion force that will look like this. We also know that there is a, we also know that there's this FZ going into the board. So into the board, rotating, look at this circular face, that force is going in this direction, in the negative Z direction. So that means we have shear from that force as well coming right along the top. And to balance that shear force, things will all look like this. And then kind of like the last problem, there's a bending stress, but since the bending is about y and we're on the neutral axis for y, we know that there will be actually zero bending stress caused by that moment at this location A anyways, right? Because A is right along the neutral axis, so there won't be any tensile or compressive bending stress along A from bending. So we're going to omit the axial stresses altogether here. But we do have two shear stresses, and the directions are important on these. We see that these shear stresses are actually acting in the same direction, so once again we're going to find these two shear stresses and we're going to add them together because they're acting in the same direction. So it's important on problems like this to keep track of the directions. So here they're going to sum. Okay, so we've got all we need now to get what our stresses are. So let's start with the first shear that we said was from torsion. We know that the equation for shear due to torsion is T rho over J. T being the torque, rho being the radius, the distance from the center of this circular cross section, and J being the polar moment of inertia. So that torque, let's look back up here to see what the torque would be. So the torque acting in the x direction, the applied torque is coming from this force Z, and that applied torque about x, the distance to the axis, the distance to the action of z is h. So we know that the torque is going to be this force multiplied by this distance h. So we'll plug that in for t. We know that t is f, the magnitude of t is f sub z multiplied by h. The radius that we're interested in is the full radius of the circle, since we're looking at the boundary. So that's going to be equal to r. And then the polar moment of inertia, we won't derive this, but we do know what it is. You can look it up or re-derive it yourselves. We know the polar moment of inertia is pi over 2 times r to the 4th. Okay, so that takes care of the shear stress from torsion. I'm going to make note of that just to keep it clear. So this is shear stress from torsion. Okay. Now we need shear stress from the transverse loading. So this will be our transverse shear. And we know that, and actually this one, if you watch the previous video, you'll know that one of the previous videos on transverse shear, we are looking at a circular cross-section, and you'll remember that when we're looking at a plane, our plane of interest has to intersect perpendicularly the boundary for us to be able to use the shear formula. So we do satisfy that here. A is the only point that we can do that for a circular cross-section for which the shear formula is applicable. And we derived what the shear stress is going to be at point A, right there along the neutral axis, in a previous video. So we're just going to write what that is. We know for a circular cross-section, for an element on the neutral axis, tau is equal to 4 over 3 multiplied by the force, which is Fz, over pi r squared. Okay? And then, like we said, if we look back at this element that we drew, the directions of the stresses are in the same direction. So for the total shear stress, we are going to add these together. And from this, since we're looking at the YZ face, this is stress tau sub YZ, right? So these two will add together to give us our total stress. Oops. And let's draw that just so it's perfectly clear. So we ended up with our stress at that point A would just have a resultant shear stress, which we'll call tau YZ, and it's the sum of the shear stresses that we just obtained. So tau YZ is equal to, if we were to rearrange this top equation for the shear stress due to torsion, that would give us 2 times Fz HR over pi r to the 4th. Oops. And then the shear stress from transverse loading is 4 over 3 Fz over pi r squared. And there's actually just a little more simplification we can do here. We won't simplify this as far as we could go, but you'll notice in this first term, the r in the numerator can cancel out with one of the r's in the denominator. So we'll end up with 2fz h over pi r cubed plus 4 over 3 fz over pi r squared. And that's our total shear stress from our load condition.